Okay, so just a quick review. This is what we are discussing. Does continual gravitational collapse, namely if the star is collapsing core is too heavy to form a neutron star, does it necessarily end in a black hole? And we are saying no, it could be a black hole or a naked singularity or a horizonless compact object or something which enters the black hole and but does not become singular, maybe goes to another universe. All right, so this is a quick summary. We first did the Schwarzschild metric. We derived this solution written in the last line. Then we showed that there is no curvature singularity at the Schwarzschild radius. We made a coordinate transformation and found new coordinates which are well behaved at the Schwarzschild radius r equals 2m equals rg. So there is no coordinate singularity. We looked at infalling light rays and we showed that nothing can be at rest inside the Schwarzschild radius. It will, if once something enters the Schwarzschild radius r equals 2gm by c square, it will go all the way to the horizon, to the center and form a singularity, right. So once inside the Schwarzschild radius, there is no escaping. And then we looked at a few interesting and important properties of what a black hole is like, yeah. And after that, we said let us study a simple case to understand Einstein equations applied to the problem of gravitational collapse. We wanted to study the collapse of a dust sphere where there is no pressure. In such a case, the infall is interestingly the same as that of a stone falling freely in Newtonian gravity. This is the solution for the distance of the stone from the center of the earth as a function of time, where capital F is the mass of the earth scaled with 2g. So it's capital F is root 2gm, and little f is the total energy, which we for simplicity took the case little f equal to 0, and this is the time at which the stone will hit the center. Then we considered a ball of dust in Newtonian gravity, which is nothing but a collection of freely falling stones. There is no pressure, so it will just fall in radially, everything will fall in radially. And we solve the same equation, except that this time the mass inside is not all at the center. It's these are like onion shells falling to the center. So the mass is a function of the distance. No, it's a function of the co-moving coordinate little r. The mass is not a function of time. So the infall of a stone here, say, or a dust particle only depends on the mass that is to the inside. In the spherical case, it does not depend on the mass outside. And we can again integrate this equation to find out how the distance of the stone from the center of this dust sphere changes as a function of time tau. Capital R is changing, little r is the co-moving coordinate, it does not change. Capital R is changing, that it measures the distance from the center. Different shells reach the center at different time, and that time is given by this singularity curve tau s of r, which is a function of little r. Okay? So that's the singularity curve. So in particular, if you want to find out when the center becomes singular, this is the mass. F of r is the mass function. Near the center, suppose the density is rho naught. The mass will grow as rho naught r cube. So the capital F function will go as rho naught r cube, and r to the 3 by 2 will cancel. This just gives you a constant 2 by 3 root rho naught. The center becomes singular at a time 2 by 3 root rho naught, where rho naught is the initial density at the center. Okay. Then we showed that this same solution works in general relativity also for the infall of a dust sphere, and this is the metric that we write down for the infalling dust sphere. There are two free functions which are functions of tau and r. Yeah, then you solve Einstein equations for these two free functions. It turns out that the equation for the infall of a dust particle is the same as in Newtonian gravity. I take a minute of pause. A, if there are any questions, and B, Patrick will do cosmology today, right? Homogeneous and isotropic universe, one of the two equations, Friedman equations, will be just what is written here. This will be the scale factor. Yeah, A dot, he'll most probably the symbol uses A or S. This is the scale factor. Little f of r is the curvature term, what you denote little k in a homogeneous isotropic universe. This object will be nothing but the density function, because in Einstein equations for a homogeneous isotropic universe, you have a density, and if it is homogeneous, the mass just grows as r cube times rho. Rho will be function of time, but it grows as r cube times rho. So this is r square. Bring the r square down. R dot square by r square equals rho plus f by r square. So you will see this equation again today. So the interior of a homogeneous dust sphere is the same as the cosmological homogeneous isotropic solution. Of course, this is more general. It is inhomogeneous. The Tolman-Bondi solution is an inhomogeneous spherically collapsing dust solution. The special case of a homogeneous sphere is the Oppenheimer-Snyder solution. Any questions? Okay, so then we studied the Oppenheimer-Snyder solution, namely the shell with co-moving coordinate little r. The shell is carrying its little r. The shell with co-moving coordinate little r is said to become trapped when its radius becomes equal to its Schwarzschild radius. Every shell has its own Schwarzschild radius, you understand, which is determined by the mass inside. Yeah, the Schwarzschild radius of this shell is 2g m of r by c square, which is what we have done. This is the solution for the case of zero total energy. This is how the distance from the center changes as a function of time. I want to know when a shell gets trapped. A shell is having a co-moving coordinate little r, which it is carrying with itself. When does a shell get trapped? When its radius becomes equal to its Schwarzschild radius. It's okay, no? Yeah? Right. So what do? I put the radius equal to the Schwarzschild radius. That's what's done here. This function capital F is nothing but 2g m of r. So I put and there is a power 3 by 2. So r equals m, r to the 3 by 2 equals m to the 3 by 2. I solved this equation to write the trapping time as a function of little r. This tells me at what time tau of t does a shell enter its Schwarzschild radius. Clearly it will become trapped before it becomes singular. To become singular, it has to go all the way to r equal to 0. To get trapped, it has to reach just r equals to 2m. At the center, the trapping and the singularity happen together. We will come to that. So is this equation okay? The trapping curve? Yeah. Look at the homogeneous case now, which is what we are studying. This equation is true in the inhomogeneous case also. Inhomogeneous means density is a function of distance from the center. It is true in this particular Tolman-Bondi solution. If initially homogeneous, it will remain homogeneous during evolution, as the density will change with time. The homogeneous case, mass grows as r cube, from the, r cube, where r is the co-moving coordinate. Put f of r as r cube here. In the homogeneous case, you get the trapping time function like this. Have a close look at when different shells get trapped. This is the Dutt, Oppenheimer, Snyder solution. Which shell gets trapped first? The outer ones or the inner ones? That is clear here. Larger the value of little r, smaller is tau of the smaller is the trapping time. The boundary gets trapped first. In such a situation where the boundary gets trapped first, there is no escaping. The fellows inside also cannot come out because the boundary is trapped. The moment they reach the light beam, reach the boundary, it has to fall back. Okay? So this is the picture for formation of a black hole. What does it say? The formation of a black hole in gravitational collapse. The event horizon starts forming at O and covers the singularity. The boundary of the trapped region inside the star is the apparent horizon. So when did the singularity form? Let us see. What is my singularity curve? This is my singularity curve, right? This tells at what time the rth shell becomes singular. F of r is going as r cube, homogeneous case. R to the 3 by 2 cancel. This is a constant. All shells become singular at the same time in the homogeneous case. Right. So which is that time? So time is along the vertical direction, space is along the horizontal direction. At this time, all the shells become singular. So inner shells I have not shown, I have only shown the boundary. So the boundary becomes singular at this time, the inner shells also become singular at the same time, and then in the future this is this wedged line is the singularity. What is apparent horizon? This region is all trapped. What does that mean? The boundary was the first shell to get trapped. Then you can see as time goes on, the interior also gets trapped, and the last ray to leave the star is called the event horizon. Anything starting here will not be able to escape. It will get trapped because the boundary is already been trapped. So this is the collapsing star. Event horizon, last null ray to leave the star. Prakash, is there any question here? Just check. Yeah. And okay, this is the space-time diagram for a formation of a black hole in gravitational collapse from a spherically collapsing sphere of dust, the Dutt, Oppenheimer, Snyder solution. If you have any questions, please ask.
It's just a question if this is what is singularity.
What is a singularity? Yeah, that's a very good question. A singularity is where the density will become infinite, and hence the curvature scalars, at least some of the curvature scalars will also become infinite. I should have called it a curvature singularity, where a curvature invariant like the Kreshman scalar diverges and becomes infinite. It is the same situation when the density at the center will also become infinite. More question?
No,
that's okay. Right. So now we get to today's part. I want to show same spherical dust gravitational collapse, but now the density distribution is inhomogeneous. The density will be maximum at the center initially, and it will fall out, it will decrease as we go away from the center. Then as the collapse proceeds, the density will start rising everywhere, but it will remain homogeneous. So density is a function of time as well as the co-moving coordinate. So recall the singularity curve and the apparent horizon curve. What are they? the time at which a shell becomes singular is given by this relation, where f of r is the mass function. Here, at the singularity, the Kretschmann scalar will diverge. The trapping time, apparent horizon curve just tells us at what time did a shell get trapped. That is this function. We have solved for this also. So now let us look at the inhomogeneous case. The center r equal to 0 gets trapped at the same time as when it becomes singular. That's easy to see. Even in the inhomogeneous case, this function is growing as r cube. So as you take the limit of the center, near the origin it will grow as r cube, then it will have different powers. So r cube power here for the mass function, this cancels. This gives me the leading term 2 by 3 root f naught, which is the same as this. So remember, even in the inhomogeneous case, the center becomes trapped at the same time when it becomes singular. We want to look at what is happening to the neighborhood. We'll come to that in a moment. For the homogeneous case, the center necessarily is part of a black hole. However, the situation is different in the inhomogeneous case. Let's write near the center the density profile as a Taylor expansion initially. The density is rho naught, the central density, and plus rho 1 r. What is rho 1? Rho 1 is the gradient, the derivative of the density profile at the origin, then higher derivatives, second derivative, third derivative. The first non-vanishing derivative should be negative. If I want the density to decrease, the first, so suppose rho 1 is non-zero, then it should be negative. How to proceed to homogeneity? Put rho 1, if homogeneous case, tell me what is the homogeneous case? Everything other than rho naught is 0. That's obvious. The density is the same everywhere and it is rho naught. As I put more and more derivatives 0, I progress towards homogeneity. Turns out I need to only look at the situation near the center. Why? All other shells are getting trapped before they become singular. If you are trapped, you will form a black hole. You cannot be a naked singularity. A naked singularity is one which is singular without being trapped. Yeah, that's what we want to check. So if I put, say, rho 1 0 and rho 2 is negative, that's little more homogeneous than when rho 1 was non-zero. I put rho 2 also 0 and I have rho 3 negative, proceeding towards more homogeneity. If you put rho 3 also 0, then start at rho 4. It turns out, as we'll see in a moment, if the first three derivatives are 0, rho 1, rho 2, rho 3 are all 0, it will form a black hole. It will not be a naked singularity. If rho 1 is non-zero and negative, the singularity is naked. The central singularity is naked. If rho 1 is 0 and rho 2 is negative, the central singularity is still naked. A very interesting thing happens at rho 3. Suppose rho 1 and rho 2 are 0 and rho 3 is non-zero and negative. A phase transition, so to say, happens. For some values of rho 3, it will be a black hole. For other values of rho 3, it will be a naked singularity. And if rho 3 is also 0, then doesn't matter. It will always be a black hole. I want to demonstrate that. It's a very simple calculation and very instructive, so it should be done. For this density function, find out the mass function. What will you do? Mass is rho r square dr. Integrate. So this will give me r cube, some constant times r cube, some constant times r4, r4 from rho 1, r5 from rho 2, r6 from rho 3, and so on. Are you okay with this? Questions? Which one? Last line, is it? This is the density is inhomogeneous. It is something at the center and then falling as we go away from the center. If it's inhomogeneous, it's a function of little r, the co-moving coordinate, and time also, but that will be in the evolution. This is the initial density profile. The Taylor expand rho of r around the center. Rho of r equals rho naught plus rho 1 r plus half rho 2 r square plus, that's the Taylor expansion. What about the mass function? Let me show you the equation. Right, look at this equation. The density is basically f prime by r square r prime. Initially, where capital R is the area radius, capital R is changing with time. I initially took capital R to be equal to little r, that's a scaling. So r prime is 1. What do I get? F is just the volume integral of the energy density. That's what mass is, no? It's a volume integral of the energy density. And that's what I did here. I integrated rho r square dr with the Taylor expansion for rho put in, integrate term by term. First term will be proportional to r cube, as you anticipate. Next term in the mass, this is the mass profile obtained by integrating the density profile. Are you okay with this? Yeah? Go on. Okay.
So, I probably miss, I did not see why it is, integration of rho 0 and rho 1 are not appearing in the mass square.
Oh, F0, F1, F2 are just rewritings of rho 0, rho 1, rho 2 with some constants. So I do this integral, rho 0 r square dr first. Yeah, this is F0 is rho 0 by 3. Yeah, you are right. I just simplified the notation. All right. Center gets trapped at the same time when it becomes singular. But what about the neighborhood of the center? What was happening in the homogeneous case? The boundary got trapped first, and then inner shells get trapped. That's what happens. That does not happen here. Question: does the neighborhood become trapped after the center becomes singular? So try to digest this. The center is becoming singular at the same time when it is becoming trapped. When the center became singular and trapped, at that time was the neighborhood already trapped or not yet trapped? Center has become singular. If the neighborhood is not trapped, there is some scope for light escaping. You get that? No. So all I need to check, then we do this more with mathematics. When the center is singular, if the neighborhood is not yet trapped, light might escape. So how do I check that? I want to check that mathematically. Near r equal to 0, trapping function can be expanded like this. What did I do? This is my trapping function. This is my mass function. This is my Taylor expansion of the mass function. Put that Taylor expansion in here. So I get my trapping function in a series which is like this, where T naught is the time at which the center becomes singular. Okay? My trapping function as a power series. Then my singularity curve as a power series, this function, do a Taylor expansion. All right. What am I asking? The center becomes singular at a time T naught. T naught is the time at which the center becomes, that is just this function, 2 by 3 root f naught, and that is also this quantity T naught. What is our question? When the center is singular, is the neighborhood trapped or not? So I have to compare these two functions, right? If trapping time is less than the central singularity time, it means the neighborhood has gotten trapped. I want to look at a situation, if possible, where the neighborhood is trapped after the center becomes singular. That is, the trapping time is more than the singularity time. You digest it slowly. Yeah? Consider the case that rho 1 is negative. The density profile rho 1 is non-zero and negative. All right? Then what will happen? F1, if rho 1 is negative, F1 is also negative. This is the first term. So this index n stands for which is the first non-vanishing density term. If it is so this is F1 R1. Yeah, no, it's not F1 R4. It's actually F1 R1 because it is coming from this. Let's see if I can convince you. This was my trapping function. I expand this. There is a r to the 3 by 2 here. So the r cube will cancel and give me 1. R4 will give me something like this. And this is how it goes. Yeah. Compare these two functions. If rho 1 is negative, F1 is negative and this is positive. This is positive and this is first power of r. So already we are seeing if rho 1 is negative, I get a positive term and this is going as r and this is going as r cube. The r term will dominate, the r cube term will be smaller. If the first derivative of the density is negative, the center will get, the neighborhood will get trapped after the center becomes singular. Similarly, if the first derivative is negative and the second derivative is, if the first derivative is 0 and the second derivative is negative, this will be r square, it dominates over this, is still positive. If the first non-zero derivative this is the line I am saying. If the first non-zero derivative of the density is negative and either rho 1 or rho 2, then the neighborhood gets trapped after the center becomes singular, in which case there is a possibility of being naked that we will examine. If the first derivative is 0, the second derivative, Prakash, any question?
Yeah, there is a question about negative, if density is negative, then matter is ghost in nature.
Matter is ghost in nature?
Yeah.
No. I have to make sure that rho naught is such that rho naught is positive. Rho naught is positive, density is falling. But I have to choose a density profile so that density never becomes negative. Only the first derivative I am saying is negative. If the first and second derivatives are 0 and the third derivative is negative, then I have still a plus term, T naught plus something r cube minus something r cube. These two terms will compete with each other. But for certain values of this number f3, if the first non-zero derivative of density is negative and is rho 3, there is still a possibility of being naked. Maybe I am confusing you. I am just comparing these two functions. If this power is r4, this term is gone, this term will dominate, and this will be R4, and this is going to be such that the trapping will happen before the singularity forms, the neighborhood trapping. So to summarize, you can just go through this. If rho 1 is negative, or rho 1 is 0 and rho 2 is negative, and rho 1, rho 2, 0, rho 3 negative, but in some particular range, there is the possibility of the singularity being naked. I will slow down here. If it's confusing, please ask me. This is the motivation. Now I'll do the maths. The maths is very clear. We now examine the behavior of null geodesics in the vicinity of the singularity at r equal to 0. Okay? What do we want? We wish to investigate if the singularity at t equals t naught, the central singularity t equals t naught r, we want to find out if it is naked, i.e. are there one or more outgoing null geodesics which terminate in the past at the central singularity? The outgoing light, if you trace it back, it emanates from the singularity. That would make it naked. We restrict attention to radial null geodesics. Let us start by assuming that one or more such geodesics exist and then check if this assumption is correct. Let us take the geodesic to have the form is radial. T equals T naught plus A R alpha. T naught is the time at which the center becomes singular, to leading order in the TR plane, where A is greater than 0, obviously outgoing. At later times it's at larger R. A naught positive, alpha, this index power alpha positive. In order for this geodesic to lie in the space-time, what is meant by lying in the space-time? Starting at the origin, going out, you should reach a location before it becomes singular. Once it's singular, you cannot talk of its propagation. So when we say for a geodesic to lie in the space-time, means the time of arrival at R should be less than when the shell R is becoming singular. There is a competition going on. And we can check by looking at the singularity curve that if the mass profile, what do I compare it with 10? 10 is my right. I have to compare with the singularity curve, which near the center is T naught my Fn R to the n. So you can see that if the proposed geodesic is going out as R to the alpha, then this alpha has to be greater than or equal to n for arriving before the center, the point R becomes singular. Why is that? Fn is negative, so the shell Rh shall become singular at a time T naught plus something times Rn. You should arrive there earlier, and it means this should be smaller. So clearly the index alpha has to be greater than equal to the index n in the singularity curve. And if alpha is equal to n, then you have to make sure that this coefficient is smaller than this coefficient. Okay. So please again stop me. I am doing something very simple. You see some algebra and some notation. All I am saying is, assume that there is a geodesic starting at the singularity and going out. See if it can escape. Yeah? To escape, it must at least arrive at a location R before location R becomes singular. What should I do next? I have to solve the geodesic equation. Outgoing null geodesics. Very simple geodesic equation. Theta phi terms are 0. If you look at the metric, you'll say outgoing null geodesics are satisfy dt by dr equals capital R prime, where capital R is the distance from the center, prime is its partial derivative with respect to little r. In order to calculate capital R prime, this function R prime near r equal to 0, we first write the solution with only the leading term. So this is how my distance from the center is behaving as a function of time. Somewhere tau has become t, but is the same object. I know the solution for distance from the center as a function of time for different co-moving shells. In that depended on the mass function. Expand the mass function in the power series that we have shown. So I know this function R capital R. Very, very simple calculation, just a little tedious algebra, not too tedious also. Differentiate this, you will get capital R prime. And I will put this in the geodesic equation. I have also assumed that geodesics exist. I made that assumption. Geodesics exist and satisfy this condition. This is my proposed ansatz, assumption for the geodesic. dt by dr is just a alpha r to the alpha minus 1. So I put dt by dr equals alpha a r to the alpha minus 1 in this equation. I have solved for r prime on the right hand side, it is this function. All I need to check is, does this admit solutions? Understand? I assumed a form for the geodesic, t equals t naught plus ar to the alpha. I put that in the geodesic equation and I want to check this for consistency. Are there any solutions? Are you okay with this? Questions? Parus? Prakash, what is the question?
Please clarify the motivation of taking the form of geodesic as an equation correct.
Ah, very good question. What else could it be, you see? Of course, you can try to do better, but I put this in the equation and I'm looking for a consistent solution. It starts at t naught, it goes out, so it should, the second term has to be positive, it arrives at a shell later than when it started, and it has, well, I think your question is good. We can do formally better. If you please look at the references that I will cite a paper, it's one of my very early papers. I will show you the citation for that paper. Then you look at the references. Your question is very good. There is a more formal proof of the naked singularity without assuming this ansatz. So please see that. That will help answer your question. Right. So I look for a self-consistent solution to the geodesic equation in the proposed ansatz. A lot of khichdi here, so I will just, I think, give you the results. We simplify this equation by putting in the requirement, that alpha greater than equal to n. This was the requirement that you arrive at a shell before the shell becomes singular. So you have to have alpha greater than equal to n. When alpha is greater than n, so we don't have to go through the maths. When alpha is greater than n, the geodesic equation simplifies to what I have written here, which now you compare powers, so which means alpha is 1 plus 2n by 3, and this a also gets read out. By substituting integral values for n, we find that only for n equals 1 and n equals 2, the condition alpha greater than n is satisfied. What was n? The first non-zero derivative. Hence the singularity is naked for n equals 1 and n equals to 2. That is for the models rho 1 less than 0 and for rho 1 equals 0, rho 2 less than 0. There is at least one geodesic given by the 11 which terminates in the central singularity in the past. If n is greater than 3, then what will happen? The right hand side, then the condition alpha greater than cannot be satisfied, right? If n is 6, let's say, then alpha is 5. So if you want alpha to be greater than n, n has to be less than, if alpha has to be greater than n, n has to be less than 3. If n is greater than 3, the singularity is not naked. This is the case rho 1 equal to rho 2 equal to rho 3 equals 0. If the first three derivatives in the Taylor expansion near the center are 0, the singularity is not naked. That is as good as homogeneous because you have simplified it. If rho 1 is non-zero and negative, naked. If rho 1 is 0 and rho 2 is negative, naked. What about rho 3? That's the most interesting case. When rho 3 is the situation we put n as 3, alpha is also 3. N and alpha are equal. This was the situation of the geodesic equation when alpha was greater than n. When alpha is equal to n and 3, the situation is this. The geodesic equation simplifies to something like this, which implies that n equals 3. So if you put alpha equals n in the geodesic equation, that is, in this equation, put alpha and n equal to each other, it simplifies to this, which implies alpha blah blah. By substituting, next slide. Right. For n equals 3, we get an implicit expression for the constant A in the proposed geodesic in terms of the density profile quantities F3 and F0. This expression can be simplified to get a quartic equation in A, and finally I get a nice little quartic equation. What was A? Remember, A is appearing in this, A is appearing here. When alpha is 3, A becomes critical. For certain values of A, there will be a naked singularity, and this A is also determined in terms of the initial conditions. Where was that? Somewhere. So, what I want to say is, my initial conditions are the initial central density F0, which rho naught, which determines F0. F3 is here. F3 is this fellow, which is related to rho 3. Now my rho 1 and rho 2 are 0, F1 and F2 are 0. So I have a non-zero F3, which is F3 and F0 are entering this equation, which will determine allowed values for A. I am not now going to find a constraint on F3 and F0 to find out when the singularity is naked. For the singularity to be naked, there has to be a solution to this geodesic equation. And the geodesic equation becomes a quartic equation for that free parameter A in the geodesic. So given that A, I define a so-called B, I define a so-called xi in terms of the initial density profile, and this is my final quartic equation, which admits positive real roots only under certain circumstances, which let me right. So the final result is that what is my xi? This last inequality is the same, okay. The quartic can be blah blah blah. I want to show you the final result. The singularity is naked provided xi is less than this number. Now let's try to see what was xi. Xi is here, yes. I want certain constraints on the initial density profile, which had rho naught and rho 3. Rho 1 and rho 2 are 0, rho naught is non-zero, and rho 3 is negative. Rho naught defines F naught, rho 3 defines F3. So it turns out, if my rho 3 and F3 satisfy this condition, firstly use rho 3 and rho 0 or F3 and F0 to define this quantity xi. This is what enters into the quartic equation. If xi is less than some number, the singularity is naked. If it is greater than that number, it is not naked. I can go back and show you some detail.
It's less than or equal to that number, right?
Yes.
What about equality? What is when the
Ah, very good. The equality is still naked. Little on the other side, it will become a black hole.
equality?
For the equality, this cortex still admits two positive real roots. That's why it's naked. Let's see. I have to then go back and look at the maths. This cortex has two positive real roots provided eta greater than equals eta 1 or eta is related to xi, like here. Yeah? Equality will admit positive. So for that, what do I have to do? I have to look at this cortex equation and find out what are the conditions for which it admits a positive real root. The equality will admit I forget the value of the root, that I don't remember now. But you can put this in Mathematica or something and ask for what values of eta are there positive. If there are no positive real roots, the geodesic equation has no solution. Then it's not naked. Huh? You just put this, I did this long ago, I don't remember now. Put this in the some code or Mathematica or even ask ChatGPT, it will solve it. Yeah, we can maybe we discuss this tomorrow. It'll be fun. Put this in ChatGPT and ask for the condition for which this has positive real roots. Yeah, you can note down this equation. So I got a bit hurried here, but you get the hang of it. This is very pretty. I like this. When we found this, we were very pleased that you see this phase transition at the third derivative, which means we have to do some seriousness about naked singularities. Maybe they are not there in nature, but general relativity is admitting it. So, there are other better examples. We can say dust is unphysical, etc., etc. This completes the analysis to decide whether or not the central singularity is naked, etc. So, okay. So, now this is a comparison of the pictures. Black hole versus naked singularity. So, left hand side is space-time diagram for a black hole. Right hand side is the space-time diagram for a naked singularity. Let's read this. The standard picture of spherical homogeneous dust collapse. First one is Oppenheimer-Snyder model 1-1. The shaded portion is the trapped region. Note that first the boundary of the star gets trapped, and the trapped region expands into the star towards the center. The apparent horizon is the boundary of the trapped region. The center is the last point to get trapped. The curvature singularity forms simultaneously all over the star. This is the first picture. Second one on the right hand side. The corresponding space-time diagram for inhomogeneous dust collapse leading to a locally naked singularity. What does locally naked mean? That I just showed that they propagate out from the center, the naked central singularity. If it escapes to infinity, I call it a globally naked singularity, visible from far. Locally naked meaning starts out from the singularity but may not escape the start. So in this example, this is locally naked. I'll show you. So what's happening is here, light is escaping from here. It's lying outside the trapped region. I'll show one more diagram. The apparent horizon curve is given by equation 6 blah blah. The shaded portion is the trapped region. Note that unlike in the Oppenheimer-Snyder model, the center gets trapped first. That's very interesting. Here the center is the last to get trapped. Here the center gets trapped first, then the outer regions get trapped. That's needed for naked singularity to form. Different shells become singular at different times, the center becoming singular first. So you can study this. This is one review article, there's a lot of other literature. And one more diagram showing in a better way formation of a naked singularity. Suppose singularity starts to form here, and trapping starts later. Just a hypothetical example. So these are light rays that can escape from the singularity. The formation of a naked singularity, the singularity begins to form at S here. The event horizon starts forming at O and fails to cover the singularity entirely. Else the singularity may form without the event horizon. You were asking, someone was asking, what's the difference between singularity and event horizon? These are two different things, two very different things. Singularity is where curvature diverges. Event horizon tells you that after that nothing will be able to escape. The last light ray to leave the star is called the event horizon. Okay? And you could have in principle, event horizon without a singularity, or a singularity without a event horizon. The Hawking-Penrose theorem say, if a trapped surface forms, singularity will form. But singularities can form without trapped surfaces also. Here is an example which so those such singularities can be naked in principle. So they gave a sufficient condition for singularity formation, not a necessary condition. So the cosmic censorship hypothesis says gravitational collapse of physically reasonable matter starting from generic initial conditions results in the formation of a black hole. Then we have to worry about what is physically reasonable. We say dust is not physically reasonable, etc., etc. And generic initial conditions, not some special arranged conditions. So why is this question of interest? Because if gravitational collapse of star ends in a naked singularity, quantum gravity will smooth out that naked singularity, but there will be very high curvature regions there will be intense particle production which could blow up the entire star. There was a time when some people thought gamma ray bursts are naked singularities. Since it doesn't form a black hole, a star, maybe if it's spherically symmetric or a merger of two neutron stars, gives rise to a naked singularity which explodes. So Ed Witten has used to say that black holes are objects, naked singularities are events. The star is collapsing to form a naked singularity. It's not going to sit there. It is very likely explode in a very energetic way. Whereas a black hole is tender. It goes in, whatever it does inside, it's okay, but at least sitting there. Yeah, black holes are objects, naked singularities are events. So astrophysically, it is definitely of interest. Not the most popular idea in relativistic astrophysics, but interesting. Maybe nature forms naked singularities sometimes. Today we know gamma ray bursts at least one class come from mergers of neutron stars. We have seen their gravitational wave signal. So that idea that naked singularities and gamma ray bursts, that is not probably viable. But we can't rule them out. We can't rule out naked singularities, and it's of interest to study their signatures, and theorists are still studying whether this hypothesis is true or not. Questions? Okay, so now to the last part of the talk. What is a horizonless compact object? So I'm not an expert in this subject. I have not worked on it, but it would be of a lot of interest to those of you who are interested in relativistic astrophysics, gravitational collapse of stars, their signatures in gravitational waves and in black hole shadows. So we have looked at two alternatives: black hole formation possibility, naked singularity formation possibility, and there's a third one even if it is beyond the neutron star state, does not form a neutron star, is collapsing further, we don't know if it will, whether or not it will stop. That is, some other quote unquote degeneracy pressure might take over, which prevents it from reaching the Schwarzschild radius. So, horizonless compact object, HCO for short, is a gravitationally compact object that has no event horizon, unlike a black hole, can have mass and compactness close to that of a black hole. Radius where it stops is just slightly, somewhat greater than 2 gm by c square in the spherical case. May avoid singularities depending on its internal matter structure. These are some in models being studied. As I said, I am not an expert, I just took this from the literature. Grava stars, boson stars, wormholes, fuzzballs. Fuzzballs, Patrick mentioned, this is the Indian name associated with it. Samir Mathur at Ohio State University was an Indian graduate student. This is his idea. Fuzzballs come from string theory. Collapsing strings stop outside the horizon. They don't go to a singularity. Okay, what kind of things we know about HCOs? Suppose you want to make a static spherical object with a perfect fluid using Einstein equations. There is such a solution known as the Bookdahl solution. Professor Dadich here is an expert on these things. You can talk to him if you like. Bookdahl star is a static spherically symmetric perfect fluid in general relativity, such that it is such, if you want to make a perfect fluid static spherical object, you can't push 2 gm by RC square too close to 1. Yeah? Black hole surface 2 gm by RC square is 1. In such an object, the Bookdahl star 2 gm by RC square has to be less than 8 by 9. Very close to 1. 8 by 9 is 0.9. You can go to 2 gm by RC square or 8 by 9, that is, the radius can be quite close to the Schwarzschild radius, but not more. Any more, then in that case that object must form a horizon. Reduce the radius below the Bookdahl radius, which you can calculate from here for a given mass, then you will not be static, you will proceed to the horizon, unless the perfect fluid condition is dropped. Some assumptions are relaxed, the fluid is not isotropic, blah blah blah. If you are making a static spherically symmetric star with a perfect fluid, the minimum radius that you can give is 9 by 8 times the Schwarzschild radius. It will be little away. Of course, we don't know if this state is realized. I'm just saying there is such a solution, but whether gravitational collapse settles into Bookdahl stars, we don't know. Right. So, to exceed the Bookdahl limit without horizon formation, matter must typically violate one or more of these so-called energy conditions. Normal classical matter, well-behaved matter would satisfy these kind of energy conditions, null energy condition or the strong energy condition, the dominant energy condition. Many exotic matter models violate one or more of these, and you need to do that to make an HCO less than the Bookdahl value. What else can you try to do? Relax the isotropy. That is, it's not a perfect fluid. The radial and tangential pressure are not equal, or allow negative pressure to enable compactness that approaches the Schwarzschild radius, right, blah, etc. Or you have to modify the equation of state to make it what is called a stiffer the better to resist collapse. dP by d rho is large. Use non-standard fields to stabilize the configuration. Ordinary matter unlikely to support such extreme compactness. It will lead to a black hole. Right. For the HCO to be physical, you don't want curvature singularities. You want to be close to the Schwarzschild radius. The interior should be well behaved. It should have smooth profiles, satisfy Einstein equations everywhere without trapped surfaces. And lastly, why has this become interesting today? Because people are finding that if they make HCOs, their observational signatures can be different from that of formation of a black hole. Even black hole, faraway observer takes infinite time to reach the Schwarzschild radius. But the horizon, the HCO will never go infinitely close to the Schwarzschild radius. In a finite time, it will stop just outside the Schwarzschild radius, and people here, like in India, Sumanta Chakrabarti is an expert. You can talk to him. He is looking at these things. The gravitational wave signatures of HCOs might be different from that of a black hole. And we are very interested. We want to know how whether black holes form at all, or is it that the things that we are seeing in the sky, the astrophysical black holes, like in X-ray binaries or the supermassive black holes at galactic centers, are they all HCOs? HCOs mimic black holes. So it's a question of fundamental interest. So as I said, this is not my expertise. After black hole merger, gravitational waves ring down via quasi-normal modes. HCOs may produce echoes due to internal structure or reflecting surfaces near where the horizon would be. Time delay between echoes depend on the location of the surface. LIGO and Virgo have been searched for such echoes, nothing yet. What is the consequence of absence of event horizon? Black holes perfectly absorb infalling matter and light. HCOs may partially or totally reflect or re-emit incoming radiation. If there is a accretion disk around, accretion signatures could differ. Surface emission versus event horizon disappearance, higher energy or variability if matter hits the surface. Tidal disruption events and compactness. Black holes above a certain mass swallow stars whole without disruption. HCOs with slightly larger radius may allow tidal disruption. Observation of tidal disruption events can help distinguish whether it's an HC or a black hole. Einstein Event Horizon Telescope, shadows. EHT images the shadow of supermassive black holes. Shadows of HCOs could differ subtly from those of black holes. Modified photon ring structure, reduced or altered central darkness. I think that is about all. Right, so this quasi-normal mode spectra from HCOs and black holes. Ring down frequencies of black holes are determined by GR. HCOs may have additional or shifted quasi-normal modes. Detections of multiple ring down modes could test this, and this is various possible signatures of HCOs. Conclusion: horizonless compact objects may mimic black holes in many respects, but subtle observational differences, especially in gravitational waves and electromagnetic emissions, may reveal their existence. So it's a very hot topic these days, horizonless compact objects. And those of you who are interested in relativistic astrophysics and data would find it interesting.
In HCOs, what is the forces that is working against gravity?
Some kind of exotic pressure. You cannot do it with a perfect fluid. You have to, 1 minute please. Right. It is some matter only, but which is maybe it's little abnormal. You have to violate some energy condition. Maybe you have to.
The known forces?
Still within GR, known forces.
What I mean, the one that is acting against gravity.
Uh-huh.
Other than the strong force, or still the strong?
No, forces are still the same, but we don't know the equation of state of matter at very high densities. It's an open question, right, Parisi? You will probably know about equations of state of neutron stars. It's an open question at very high densities. So there is scope for playing around with the equation of state mainly.
Even with quark stars, I think they are not that compact. That
Which stars?
quark stars.
Okay, the quark stars are not HCOs, is it?
HCOs, I assume that the matter is within the traditional Schwarzschild event horizon, or is it?
HCO is just outside the event horizon.
Oh, just out.
Just outside. Once you are inside, you will go in. So it's like 2gm by c square plus little bit.
Okay.
It does nature prevent black hole formation?
But then HCO is, I mean, everything HCO which is not a black hole.
Yeah, but like after the neutron star state, they would tell us neutron star maximum mass is 2.4 solar masses. Suppose the collapsing core is heavier than that. Is there something to still halt the collapse? I agree everything is an HCO other than black holes, but how HCO are you? This is very important.
So consider
HCO is a black hole mimicker. The sun is not a black hole mimicker. Things that I call HCO mimic black holes. They go very close to the Schwarzschild radius, but they don't get there. So this, let's say, takes any famous black hole, I don't know, I don't remember these numbers, take some astrophysical black, Cygnus X1. Has the co-moving observer has the freely falling observer crossed the Schwarzschild radius and gone forever, or he is enjoying himself just outside? In which case it would still be very dark, emitted light would be very highly redshifted. It's mimicking a black hole. I think it's a question of great interest. Do you have a black hole there, or do you have a black hole mimicker? It's a very interesting question.
What is the mass of that
HCO? Well, anything greater than neutron star mass limit 2.4 solar masses, in principle, could work as far as I know. Anything less than that, it will remain a neutron star. We want to cross that limit. Maybe 10 solar masses. Even HCOs have not been found, so can't say anything.
Another thing is, as people treat it as hypothetical objects. So how, like in black holes, we say that there is event horizon and singularity at present. But we treat in like the SCOs, there is no event horizon and singularity.
No event horizon, no singularity. Think of it as an ultra compact star, more compact than a neutron star. From far away, it looks like a black hole. But maybe if you probe very carefully in gravitational waves and in event horizon telescope shadows, you may be able to say, oh no, this is not a black hole, it's a HCO. Your people are now talking of fine-tuned signatures, observational signatures, which may distinguish black holes from black hole mimickers. Earlier it was not possible because we did not have these observatories, but now it's become interesting. No, go ahead, what are you saying?
So, I mean, we just assume it, any experiment on it.
No, not yet. They may not exist. Black holes, see what I'm saying, something is there in the sky which looks black. Is it a black hole or is it a black hole mimicker? I mean, I would say there's no reason to believe that it's a black hole itself. Even gravitational wave mergers have detected a darkness, but maybe the experts can say better.
So how certain we are that what we are seeing is a black hole?
Yeah, I don't know if somebody else knows. I don't know the answer to that. How certain are we that what we are seeing is a black hole and not a HCO? To my understanding, it's an open question.
Would it still have a magnetic axis?
Say that, please.
Would it still have magnetic axis like Newton does? They have it's a regular system.
Yeah. So that's why people are trying to look at observational signatures.
And the Abelgas that was awarded to the EHT image, they refrained from using the word black hole in their
Yeah. What did they call it?
supermassive central object
Yeah. That's an HCO.
in the galaxy.
Yeah. This is the gaze, Andrea gaze. That one, is it? Yeah. So,
Even in that one, we don't know for sure there is a
but that's not EHT, no? That's stars going around.
That one, the one that was awarded to the observations of
Andrea Gaze and Penrose, that one.
Oh, sorry. So the So the EHT, it was awarded after the EHT observations.
EHT has not got a Nobel Prize, but that's okay. That's it. But you are right. The EHT guys may not have called it a black hole, but
Within the scientific community, they were all saying the observational evidence for a black hole and all. Following which, when this Nobel Prize was awarded for Andrea Ghez and then also Brian Argyle, they refrained from using the word black hole.
Yeah.
Okay, make an argument for solar mass or of the order solar mass HCO, but can you make an argument for a supermassive HCO?
I don't have an expertise on this. It depends on how supermassive black holes form.
Then you're talking about compressing billions of solar masses.
No, but that's about how supermassive black holes form. If they form, maybe they form by eating things, or they form from mergers of smaller black holes. I don't know.
No, the point is that we say that supermassive compact object is a HCO. We have to hold up so much the gravitational forces.
The point they cited was you are not clearly imagining the black hole at the center of the galaxy. You are mostly dealing with orbits around the central object, and you are concluding that you have a lot of.
I think we have.
So they just said supermassive central object.
What Prakash is asking is, okay, just little heavier than neutron star, maybe collapse, halts outside the Schwarzschild radius. What forms a supermassive black hole? It clearly is not a gravitational collapse of a supermassive object. Supermassive black holes, as far as I know, form from eating up a lot of matter. So,
My point is just physics-wise,
okay, yeah.
think of much stronger forces than just a strong force to hold up billions of
Yeah, the point is, at least in the case of just beyond neutron stars, you may say strong force, but we don't know the equation of state at very high densities. So you are asking now, if a supermassive black hole, what would make it an HCO? I have to look this up. I should not speak much.
The forces you require would be orders of magnitude higher than anything.
Maybe you are right. Maybe you are right.
Billions of solar masses.
So supermassive black holes, you are saying, are black holes, but not HCOs. What Paris is saying is, even the Nobel Prize citation did not call.
I'm just saying.
Maybe it's funny, because then Penrose Nobel Prize is for predicting black hole, which is also not correct to state that. He showed that trapped surfaces, if they form, lead to singularities. But singularities are not black holes, they are not necessarily covered. There also the citation is a bit off. It is as if Somehow they wanted to make that Nobel Prize all about black holes, but let's read up. I will look at it. Your point is very good. Maybe supermassive black holes, whether they are HCOs or not, I have to look up. I don't know.
It's not a scientific argument, it's just this
No, your point is good. Yeah. Well, what exactly is going on? Yeah.
simplest explanation is it's a black hole.
Yeah. So what if it becomes supermassive by gobbling up material and other stars?
Even then,
Yeah. I don't know. I have to see this. You may be right. Yes. Any question? Okay. Yes. I thought I'll do one more lecture, but maybe not.
we can ask questions.
All right. So
What is the equation of state of HCOs?
it's a open issue. You may have to violate the so-called energy conditions which normal matter satisfies. So I think some people even talk of a dark energy kind of. It needs to be what is called very stiff. If you have P as something rho, that something should be very large. The pressure density gradient should be very large, but it's all open. There's no well-defined HCO. Let's say it's an open research topic. People are investigating what equations of state might form an HCO within general relativity. You are interested in the topic?
Yeah, actually I am working in the Java stuff, but now it's my starting stage. So
Well, you already know more than I do, so you please tell us about gravastars. What is a gravastar?
yeah, Java stuff like alternative of black holes, in which there is no event horizon and it's totally singularity.
No, what's the form of matter?
Actually, here we use the equation of state like P equal to omega rho.
Mm-hmm.
So the interior, the gravastar is consists of three parts: that interior and intermediate region, and another one is exterior region. And the interior region is described by de-Sitter condensation phase.
Described by?
De-Sitter condensation phase.
Can you say that? What you should say?
Is it a condensate phase?
De Sitter condensate. Ah, okay. That's like a negative energy equation of state. Yes.
And the outside is described by the Schwarzschild matrix.
Okay.
And I mean, whatever all that things we work in that physical teachers, all that things, we work in that things.
Yeah. I understand it. A negative pressure equation of state like dark energy, if it were to arise, it would repel gravitational collapse. And like a little bit like Einstein's static universe, you are stopping the collapse by this negative pressures which will which will repel gravitational collapse. Acceleration in the opposite direction.
If you consider such exotic objects, then yeah, you could probably have a supermassive HCO.
Yeah, I agree. Maybe this is a bit speculative. First thing I should say is I'm not an expert on this. Maybe Devasita knows more, I think.
No, but it is still very speculative.
Yeah. So it has become interesting because you can check for it in the data. Gravitational waves, black hole shadows. That's why it's become interesting. Maybe invite Sumanta sometime to give a talk on this here.
Devarati Chatterjee over here, along with the group's work on this equation of states. There is a large catalog of all different possible equations of state which are available in the literature, and they formally put it together in some database. And through GW observations or other observations that keep coming in, they try to rule out some of these and try to constrain what the equation of state might be.
For neutron stars or for HCOs?
No, they do it for neutron stars, but then in the neutron star domain, they also try to look for different compositions of neutron stars and vary different parameters of the internal composition. So they also, my brother is working on that, where he explores exotic matter.
He works with her, is it?
Yeah,
I see.
and they try to look at, say, boson stars or different compositions in the cores again and vary the fractional
This
composition.
leaves a signature in the gravitational waves, is it?
Yes.
After neutron star merges.
Yeah.
Okay.
And so they will vary all these parameters and try to constrain the interior composition of neutron star by constraining the equations of state first, but there are a large number of possibilities. And like the dark energy part that you were saying, there's also this possibility of dark matter being accumulated in the center of the neutron star, which can further bring about a whole
So maybe those interested in HCOs can make use of such catalogs. Yeah, so maybe you should talk also to Professor Debrati, and that would answer your question better than mine. Yeah. I think, Prakash, it's worth studying because end state of gravitational collapse is a completely open area. That it forms a black hole is a folklore.
But if you're conservative, you would try to say how well can we be certain that it's a black hole. If you're very liberal, then you would.
I would start with a clean slate. Neutron star degeneracy pressure has been overcome. Collapsing core is more than 2.4 solar masses. Now work. Let's get down to work. Yeah. Supermassive, I don't know. I think we have to. There's a lot of work going on how supermassive black holes form. So we have to talk to those people.
I
Yeah.
didn't think about this, some sort of dark energy sort of thing. I mean, at least in theory makes sense.
Yeah, if you ask me whether I would work on it, probably no. I wanted to work on other things, but I think it's a very interesting thing to work on.
As far as supermassive black holes are concerned, like apart from the direct formation, the merger theory is also something that I've heard is being favored, but that is slightly at a disadvantage because of the internal mass black hole gap.
There's a mass gap. Yes. So what is favored? That it forms as an end state of something, is it?
Merging black holes rather than a direct gravitational collapse.
The mergers are favored, no?
But
Yes.
because of the lack of detection by IIBHS.
Again, we have an Indian expert on that, I think Priyamvada Natarajan in Yale. So maybe anyone interested in supermassive black hole formation can get in touch with her. But good point, Prakash. Let's think it over. Maybe we discuss it tomorrow. What's the deal with supermassive black holes? Can they be HCOs or not? But what you seem to say looks reasonable. Yeah. I don't know if we have foolproof evidence for a black hole. I don't know.
That's valid inquiry. I think there's a slightly long question on the chat.
Okay. Last one. Why do we study the observational signatures of HCOs considering it to be mimicking black holes? The fundamental difference lies in absence or presence of horizons. What is the point of comparing their shadows, quasi-normal modes? Unfortunately, I don't know as I said, I'm not an expert. Depending on whether or not the horizon is present, the infalling matter would give different signatures, both in shadows as in quasi-normal modes. But what exactly is the difference and what causes the differences, we will have to ask some expert. Previous question? And before that also something is there. We know that the ultimate fate of gravitational collapse within GR is either a black hole or a naked singularity or an HCO, I am saying, depending on the generic initial conditions. Is it possible to get a hypothetical astrophysical object like wormholes, horizonless under different initial conditions as a final fate? A wormhole would, to me, would mean the freely falling observer enters the horizon, doesn't hit a singularity, escapes into some other universe. That would be like a wormhole. In principle, I think that possibility also exists. I mean, I wouldn't rule that out because it might involve some quantum gravity effects. Yeah. Anything before this, Prakash?
No.
Yeah. Then rest is okay. Yes.
Do wormhole solutions, they have horizon or they have?
We are now talking about the freely falling observer who's going in, not from the point of view of a faraway observer. And yeah,
Horizon just means some sort of point of no return for all geodesics.
yeah, but this guy is going in and going somewhere else.
But horizon is
Yeah. So as far as I can see, I mean, there could be a horizon, but what is the kind of situation we are experimentally or in the real world interested in? I wish there was time to do my last talk. I had chosen a topic which I thought would be quite interesting. Let me at least, my time is up, so I won't do the talk, but it is related to what you asked, so I thought I can at least display it. I wanted to do this today. If there, if there is time, I can do it tomorrow, because I also have a little bit of guilt feeling. I'm supposed to give 10 lectures. I've covered 9. I haven't done the 10th one. So, but tomorrow is their day. So what is the kind of thing we are interested in the real world? I mean this in a serious way. We are here. Andromeda is whatever 20 million light years away, some big number. The kind of thing which seems to arise in our work is that there is between any 2 points in space-time, there is a shorter path through what is known as a second space-time. So if I am here, Andromeda is somewhere else, there is a second copy of a 4-dimensional space-time which has 3 times in one space. We have 3 space in one time. That fellow is having 3 times. This is not a joke. It's a serious business. I mean, I would have explained it if we had time to give this talk. And in that second, every 2 points in our universe are also in the second space-time. And there the distances are very small by some 26 orders of magnitude. So Andromeda is maybe a few centimeters away or something like that. But to probe that, you need a new force. You need this force we call dark electromagnetism, which has these corresponding gauge bosons, which are called dark photons, which follow that path. And that's what we call a quantum wormhole. You have to be quantum systems to communicate through that. It is a way to solve the EPR paradox, which again we didn't cook up, it came out of theory. So there is a problem. Quantum non-locality puzzle is a problem. Namely, if you have a pair of correlated particles, an electron and a positron, the electron is here, the positron is at Andromeda. You do something, make a measurement on the electron, positron is instantly influenced. That is a fact. It has been observed in experiments. How do they do it? How is there an influence as if something faster than light influence travel? one good way to think of it is, no, relativity still holds. Influences travel only at the speed of light, not faster, but there's a shorter path. The distance is less, the speed is still the speed of light, and every two points in space-time are connected by these two channels. The other channel is accessible only to correlated quantum systems, and there's a the so-called dark photon which travels from, I'll come to that, from Alice to Bob, so to say, in the EPR experiment. And that is something like a wormhole. I wouldn't rule out the existence of such quantum wormholes, which are basically a modification of space-time structure by going to higher dimensions. Higher spatial dimensions have not been seen, I agree. But what are higher time dimensions? They are compact with a time radius of around 10 to the minus 26 seconds. You can travel to the future and come back in 10 to the minus 26 seconds. You can go to the end of the universe and come back. Such things are not ruled out. So there is one global time, which is our time, which is measuring the age of the universe. But we cannot rule out that there are extra times which are closed and below the current time sensitivity measurement, which is around 10 to the minus 19 centimeters, minus 18, minus 19. It has some number, pico, tero, some such name is there. That's around 10 to the minus 18 seconds. Anything below than that has not been yet measured. So we are claiming there are no time intervals smaller than 10 to the minus 26 seconds. So we are making an experimental prediction which can be tested. And on that time scale, you can go to the end of the universe. Nothing can rule that out, and the EPR paradox tells us that such a thing may be possible. The reason why Alice and Bob managed to communicate is because there is a path, like a tunnel or a quantum. Such wormholes will not have horizons. They are actually, you can go, I'm not saying a human being can go in. You have to be an elementary particle of the size of 10 to the minus 16 centimeters or smaller, the weak interaction scale. So you cannot send human beings and spacecraft through those paths unless you can, become diminutive. I can make me very small and send me through that, and then I become my normal self again, something like that.
Are they called wormholes?
The name quantum wormholes is we have given it that name because, well, it looks nice. In our paper, this is the paper. We call this a quantum wormhole. It's very recent, just few months ago. But I'm not saying it is true. I'm saying it's a proposal which is worked out, which can be tested experimentally. We predict this new particle, a dark photon. So we should look for dark photons in colliders. And it comes out of theory. We did not invent extra times to solve the EPR paradox. Something else we were doing, trying to make some unification, predicts the space-time to have 6 dimensions, 3 of space, 3 of time. Our universe is a subset of that, 4D. There's another subset which is also 4D, but only quantum systems see that. 6D is made up of 2 4Ds, overlapping 4D subspaces, and that other universe might be giving us these short paths.
The main motivation was to resolve the EPR paradox?
No. We were actually doing something in quantum foundations, like a quantum theory without time. If you remember in my first talk, I said that there should be a reformulation of quantum mechanics which does not use classical time. To build that formulation, we went sort of step to step until we reach a situation where we say that actually there are 6 forces in nature. That says something about particles. It's not 4 but 6 forces. One of them is this dark electromagnetism, also called dark photons, possibly responsible for MOND. We talked yesterday, I think, and talk to you, Res. Right. So from there, we say, oh, if space-time has 6 dimensions, maybe we can put it to use. If the extra dimensions are time-like, then you get an extra path. So what is happening is in the 6-dimensional, so what's the problem with EPR? Space-like separated events seem to influence each other. That is, you are outside each other's light cone, but you are still influencing. That's not allowed by special relativity. So there is a apparent conflict between special relativity and quantum mechanics because of the EPR. That's why they wrote that paper, Einstein, Podolsky wrote it. We are saying if you have a 6-dimensional space-time, the 2 events are actually not outside their light cone. They are inside their light cone in the higher dimensional space-time, but when projected to our 4D space-time, they look like as if they are outside each other. So special relativity is not violated, but you need extra time-like dimensions. So in a way, that's a very conservative solution to the EPR paradox. No violation of special relativity, no modification of special relativity, no modification of quantum mechanics, just modification of space-time, extra dimensions. And it's testable, it can be ruled out.
So your dark photons are massless?
Yes, it's massless. It couples, like we talked yesterday, to square root of mass. But it's massless, yes. It is the brother or sister of the ordinary photon. Now, photon couples to electric charge, dark photon couples to square root of mass.